Okay, so yeah, uh, is my screen visible?
Yes.
Yes, good, visible.
Yeah. Okay. So now let's. So what we were looking at in the last class was this the motive of going through this entire discussion. Okay. The motive of going through this motivation behind going through this entire discussion is that if you apply, see the point is if you apply a certain electrode potential to the it's a certain potential to the electrode, that means in an electrochemical sense potential is always equated to energy being either supplied to the electrode or taken out from the electrode, like in case of charge being supplied to the electrode or taken out from the drain from the electrode. But nevertheless you are manipulating the energy levels on the electrode side, and thereby what is the influence of that manipulation on the rate of the reaction, here the rate of the interfacial reaction, and therefore the Faraday current which is flowing across the interface. Okay, Faraday current which is flowing across the interface through the system. So this is our motivation. Once we understand this, then we can we have the power to manipulate as intrinsically, even during the argument what is coming out clearly is that it gives us the ability to manipulate the rate of the reaction. So you can make a drive a reaction which is very sluggish, very kinetically very slow. You can increase the rate of the reaction, or vice versa. If you want to slow down the reaction, you can do that as well by purely manipulating the electrode potential. Once we establish this triangular relationship, this relation is more popularly called as Butler-Volmer equation. There is the names of two scientists. One is Butler is actually, as you can guess, it's English physicist actually, and Volmer is, I think, from France. So their combination is actually what was the reason why this is called Butler-Volmer relation is because they were the ones who actually started to look at this side of the equation, and they derived the empirical rules that we still follow today. So now, in order to understand this, we do a Gedanken where we have the step 1 where we consider the reaction as a purely chemical reaction. That means at time t equal to 10 power minus 14th of a second, if when you create the interface, the electrical field is 0, and so the electrical double layer, the concept of electrical double layer is not there, mainly because the electric field is across the interface is 0. So the ions are not yet felt the presence of this electrode. So the electrolyte into which this electrode is dipping, the ions in the electrolyte, the both positive and negative ions, have not yet felt that there is an electrode that is being dipped into the solution. So that is, and we have the right to do it as long as we stick to the fundamental principles. We don't violate any fundamental principles. We are only doing a thought experiment. If you were to ask me whether in reality you would be able to track this, we are getting close to that, but not exactly there. We can now do this to look at reactions, say for example purely chemical reactions with the resolution time, with the temporal resolution, that means with a time resolution of 10 power minus 12 to 10 power minus 13 seconds. This is we are looking at 10 power minus 14, so we are very close to that experimentally. Of course, when this was formalized, this was not 10 power, even microsecond was a challenge. Okay, I'm talking about early 1900s. So even microseconds, looking at a reaction in microsecond time interval was a huge challenge. So people were not, and they thought, okay, 10 power minus 14 seconds at that point of time was equivalent to almost infinitesimally small time resolution or time step that is involved. So they said 10 power minus 14. Once we experimentally can achieve 10 power minus 14 seconds, then we might have to push this time and say that maybe 10 power minus 18 seconds. Okay, nevertheless, it remains a thought experiment where you see that at time equal to, at an infinitesimally small period of time, as soon as you immediately insert the electrode into the electrolyte, your electric field is 0, EDL is 0, but then there is the reaction. Say for example, you are interested in converting A to B. This reaction is now, because this electric field is zero, there is no electrical or electrochemical contribution. This can be visualized as a pure chemical reaction, and there is a delta G naught associated, or a potential energy barrier associated, which is with this reaction, which is purely in chemical terms. So the barrier associated, or when I say barrier, it is actually the activation energy. Okay, activation energy associated with this conversion associated is purely chemical in nature. There is no whatsoever contribution of electrical picture here. So then you can write your overall rate, which is a chemical rate constant, as kT by h exponential minus delta G naught. If you want to put double dagger, it's fine, by RT. This is the chemical rate constant. So this symbolizes this. This is the same rate reaction which I have written, like which we have studied through classical chemical kinetics. So this is the chemical rate constant. Only one thing which I want to emphasize here is this k here is what we defined as jump frequency. Okay, jump frequency. It depends on, again, which book you follow. If you follow, I think, Bard and Faulkner, they call it as jumping frequency, and Bokris and Reddy calls it as jump frequency. So please don't get confused. These two signify the same term. Okay, depends on which textbook you follow. Okay, so the jump frequency, what is exactly the jump frequency? It's, again, we are not deviating anything from chemical kinetic considerations. We are still completely within the rules of chemical kinetics. We are only relooking. Say for example, if you say that the chemical kinetic, the rate constant is say 5 per second, or in general x per second, what it means is that the per unit time, that is in this case 1 second, what is the number of occurrences of the jump. What is the jump referred to? Okay, please stop me at any point of time if this is not clear. Say, well, for example, if I say that some reaction has a rate constant of 5 per second, that means in 1 second there are there is 5 occurrences of either the reactant going to the product or the product going to the reactant. Doesn't matter, depends on how we define the rate constant, whether it's the forward rate constant or the backward rate constant. But here we are talking about a general rate constant, so it could be either one, but just that in unit time there is the number of occurrences of that jump, one species jump into the other is 5, or in a general word is x. So that is exactly what we call here as jump frequency. The only point of difference when we want to employ this concept of chemical kinetics to electrochemistry, subsequently we will see that this jump frequency, the reason why we have not defined it as a rate constant but rather calling it as a jump frequency is because we are interested in the charge jumping across the interface in one way or the other. Okay, either an electron goes from the electrode and becomes a charge on the electrolyte, or the charge from the electrolyte jumps over to the electrode and becomes an electron. Okay, so we are interested in the charge jumping across the interface, and that is why we have given this so like kind of a reworded or renamed the rate constant as a jump in terms of jump frequency. Okay, so now this is the step 1 where we are looking at purely chemical reaction. Now on top of this, in step 2, we say that step 2 is looking at something like a longer time situation, say maybe 10 power minus 10 to 10 power minus 12 seconds time interval. That means you sample the system at every intervals of 10 power minus 10 to 10 power minus 12 seconds. This gives it enough time for the surface excess charges to create a non-zero electric field. The electrical double layer as a result of the electric field that is imposed, the electrical double layer also starts to build up. The reorganization of the ions on the electrolyte side happens. We have looked at in detail about how the electrical double layer forms, what is the driving force, and so on and so forth. So essentially, the sampling time now becomes a slightly larger or longer sampling time. So that means we are now able to visualize, or the effect of the electric field, which is in turn originating from the surface charges, is now starting to manifest itself across the interface. That means the interface is also now starting to react and thereby form the electrical double layer. Now the central question is, what if we have the electric field, what is the effect of the electric field, which is non-zero electric field, on the rate of the reaction? So we are actually breaking this down, this Butler-Ulmer triangular relationship. We are breaking down into, or rather deconvoluting it into two parts, two fractions, so as to say. One which talks purely about chemical rate constant. That means what would be the rate of the reaction in the absence of an electric field. Then you try to understand how would that rate be changed in the presence of an electric field. So then if you understand these two together, put these two terms together, then you will understand what is the rate of the reaction in presence of an electric field, which includes the chemical rate constant term also. And thereby you will see that what is the overall rate of the reaction, and not just the rate of the electrical field alone, or not just the rate of the chemical reaction rate alone, but a sum total of all these things. What would be the effect of the electric field on the overall rate of the reaction? That is the argument. So far things are fine. Yes, are you able to follow the kind of argument that is being made, the flow of the argument rather? Okay, the direction in which we are trying to take this forward. Is this clear?
Yes.
So, I want to ask that
Yes.
the general expression for rate constant that you
Can you be a little louder? I'm not able to hear you.
yeah, the general expression for rate constant that has been written from the Arrhenius equation that you have written here.
Yes.
H by H. So here we can see T and delta G are the only two parameters because everything else is a universal constant. If I just find out some barrier from the electrostatic term, I can just modify this equation, right?
Exactly. That is what we are going to do.
Okay, so we have to now find a barrier value.
Yeah. We will come to that. We will come to that. Yeah. I'm happy that you raised this question. So this is something which we are going to discuss more. Okay.
Yeah. Okay.
Yeah. Excellent. So then, see, now again, I'm just redefining the term. Of course, I have to write the Ca here. That is the concentration of the reactant. Okay, that if I put a rate law, then concentration should be there. So here, what we are seeing is that in the absence of an electric field, this barrier represents the chemical barrier. The delta G naught represents the chemical barrier. It's a purely chemical barrier because we are not talking about a spontaneous reaction. If the reaction were to be spontaneous, then there is no problem, that nothing that we need to talk about it at all. Okay, so there is spontaneous reactions are you just put the reactant to even if it's a single reactant system, then you put the reactant and you will eventually get the product. That is not what we are interested in. So the chemical reaction also has a barrier. Now, like I said, in the absence of the electric field, this rate constant is going to be this, which is which is what we defined as the jump frequency, and therefore the overall rate of the reaction is that the nu C, the chemical rate constant, the chemical rate of the reaction is the chemical rate constant which we have seen here, multiplied by the concentration of the reactant for a reaction A plus going to A. okay, for a reduction reaction, A plus going to A. So now we are also simultaneously plotting, making a energy profile plot where you see how the potential energy changes with respect to distance from the electrode. This distance from the electrode can be any distance here, because we are just the distance from the electrode is actually meaningless, because we are defining everything in the absence of electric field. But the only reason why we put the distance from the electrode here is because the reaction, the chemical reaction, even if it is a purely chemical reaction is capable of occurring only at the interface. And that is the only at the interface. That is the only reason why we have put the x-axis to be distance from the electrode. Otherwise, it could be just an energy. If you replace the distance from the electrode and write it in terms of the reaction progress, okay, like what you do in a conventional chemical sense, the reactant going to product or product going to reactant, whatever, the x-axis is always a reaction progress. But only the difference or only modification that we have done from that picture is that we have taken out the reaction progress coordinate and replaced it with the distance, electrode distance coordinate, because even if it is a chemical reaction that we are interested in studying, it is still happening only, it is still capable of happening only at the interface. That is the only reason why we put the distance from the electrode here. It has no bearing on the rate the rate of the reaction or the rate constant of the reaction whatsoever, because we are not considering the presence of an electric field. The electric field is absent here. Is this fine? Is this clear? Is this clear?
Yes.
Hello?
Yes, this is clear.
Everybody is with me on this?
Yes.
Everybody is with me? Every single one of you?
Yes.
I don't want one yes or one. How many of you are there? 44, please. 44 people giving me one S is hard to digest. Okay, so I'm assuming that, okay, things are clear so far. Okay, so the only modification we have done to a conventional chemical potential energy surface or a potential energy profile is that we have replaced the x-axis. Instead of writing it as a progress of the reaction, we are replacing the progress of the reaction with distance of the electrode, distance from the electrode. X is equal to 0 signifying the electrode itself, and x is equal to infinity signifying the bulk of the solution. So now, given that every single reaction that we want to drive, every single atom or molecule that we want to drive the reaction to, that is every single ion, in this case A plus going to A, the reduction reaction, for every ion of A that is getting converted, every ion of A plus that is getting converted to A, you will have the reaction happening necessarily at the interface and nowhere else. Okay, so that is the only consideration that we have made, so that we put the distance from the electrode. Okay, so then now, like I said, there is going to be, with this kind of an energy profile, this is purely again a chemical energy profile. Now we do the second step, that we impose the electric potential on top of it. So here what I'm doing is the x-axis is common here. The distance from the electrode is the x-axis. Okay, now on one hand you have a potential energy which is or the free energy which is shown in this profile. Okay, so this is the energy profile of the reaction, and because we are doing it at the interface, you have the OHP. I've put a dotted line. This is the OHP, the outer Helmholtz plane. Okay, now on top of this, at the same instant of time, we are adding the step 2. So at at t equal to 10 power minus 10 to 10 power minus 12 seconds, at this time interval, Okay, the previous picture was at t equal to 10 power minus 14th of a second, so no electric field. Now we are slowly moving out from that and saying that what happens if I put the electric field or superimpose the electric field on top of the energy profile. All I'm doing is I'm superimposing the electric field that is created at the interface. It could be the electric field due to the surface charge of the metal of the electrode itself, or it could be an electric field which is created by connecting the electrode to a DC power supply. Either way, we are creating an electric field across the interface, which is going to manifest as an electric potential. And because we are interested in the occurrences or the dynamics very close to the interface, outer Helmholtz plane, which is sitting roughly about 2 to 3 nanometers away from the interface, is large enough distance so that we can monitor this within this space. So this is x is equal to 0, this is x is equal to 3 nanometers, and this is x is equal to infinity, which is bulk. So we are interested in looking at what can happen very close to the interface. So we take the outer Helmholtz plane as the outer bound. We are not beyond this. The electric potential is going to definitely exist, because the Stern model or the Goy-Chapman modification says that after this, the potential varies in an exponential fashion, decays in an exponential fashion. So that means it never goes down to zero. Actually, it becomes infinitesimally small. But within this outer Helmholtz plane, you have a linear decay of electric potential, or linear profile of electric potential. Okay, so what we are trying to do is take it in. This is slightly unconventional representation, so that's why I'm stressing on this again and again. Your x-axis is distance from the electrode. That means you are looking at it spatial. You are looking at the spatial resolution. Okay, you are looking at space from the electrode. If this is the electrode at a distance of 3 nanometers, what is the kinetics or what is the dynamics of the system, how is the dynamics of the system evolving within this spatial domain of x is equal to, starting from x is equal to 0 till x is equal to 3 nanometers. Within that spatial domain, now you are going to contend with an energy profile domain and an electric potential profile. Okay, so there are multiple things that are being superimposed. One, you are first considering a spatial domain of 3 nanometers thick spatial domain. Within that, the first thing you are putting is an energy profile. The second thing you are adding is a electric potential. And the reason why we are considering both in the same spatial domain is because we want to study, if you introduce an electric potential, what is the effect on the energy, what is the effect of the electric potential that is introduced on the energy profile. Okay, so that is what we are, because I'm probably repeating it multiple times in multiple different ways, because I want you to get the question very clear. If half the concept is about understanding the relevance of the question, importance of the question, and then remaining half of the argument becomes a cakewalk. Okay, so the electric contribution to the work done by ion in overcoming the barrier. Okay, in overcoming the barrier, and that is what we are saying as the ion moving from the initial state to the final state on the metal across the interface. The ion jumping from the solution, because remember we are talking about a reduction reaction. That is the system that we have taken here, A plus going to A. So for the reduction reaction, the ion coming from the solution is in its initial state, x is equal to infinity bulk state. It is moving across the towards the interface, and then in the OHP part, it has to undergo an energy profile, that is cross over the energy barrier. If it were to be purely chemical, it has to cross over energy barrier before it becomes a part of the metal. It gets reduced, A plus getting reduced and becoming a part of the metal. It is now a atom which is sitting on the metal surface, on the electrode metal surface. Okay, so for that to happen, you have an energy profile, and the same spatial domain, you are now having an electric potential also playing its role. Okay, so then what we are going to do is, if you see this, now let us say this is A plus, the ion which is sitting at the outer Helmholtz plane. At this point, it has now already become got reduced and become a part of the electrode. Okay, I'm again redefining this. X is equal to 0, X is equal to 3 nanometers here. Now, why is this alpha is coming here? I don't know, some animation problem. Okay, so now we are considering everything, all the dynamics that is happening in the OHP. Now as the A plus starts moving towards the interface, you now see that it has to climb an energy barrier. Now the interesting thing is, even again drawing from principles of chemical kinetics, it is enough that you supply this the energy, that is why it is called as the activation energy, or the delta G naught double dagger. That is, if you supply this activation energy, it is enough that you supply this activation energy so that this A plus goes over to A plus on the in the transition state. That is, if you climb a mountain, say some analogy to easier way to visualize this is, you are pushing a ball up a mountain. Okay, now the energy that you are supplying is only enough, you need to supply only that much energy that will take the ball from the ground level to the top of the mountain. The remaining, after that, whether the ball rolls this way or that way, that means whether the A plus in the transition state rolls this way or this way, it doesn't matter to you. In effect, what we are saying is that the energy that you need to supply to the system is only this activation barrier, is only the energy that is required to cross the activation barrier. Once it reaches the summit, whether it crawls over to this side and becomes the product, or rolls back and forms the reactant, is something which we don't know, and which we don't really bother about at this stage. Okay, so then if you look at it, because this is superimposed, the energy profile is now superimposed on the potential profile. Okay, now if you see that the corresponding, if you draw a vertical line and say this is the place where it cuts the distance from the electrode, you will see that because this potential profile and the energy profile are superimposed, is exactly overlapping one on top of each other. That means, and now because your potential profile is linear, we are considering only things which is happening inside the outer Helmholtz plane. So that means the potential profile is linear. So you have a delta phi, which is the potential which is existing from the interface till the OHP. The potential drop across the interface is delta phi. But what is interesting to note here is that you need to supply only a small part of the energy. That means the energy, the contribution of the potential profile to taking this A plus, which is sitting at the OHP, and taking it till the transition state. That is the energy that you are needing to supply, and only that part of the potential profile is going to do the job. This part, or rather, if I want to plot it the vertical way, this part of the potential profile is what is going to provide energy for A plus to go to the transition state. The transition state, which is the peak of the summit. Okay, not this. Are you able to see this? That means I'm sitting with a potential difference of delta phi, but turns out that not all of the delta phi is required for the reactant to go to the top of the summit. Only a fraction of that energy is required for the reactant to move to the top of the summit. Is this concept clear? Okay, so then what is happening is only a part of the delta phi is relevant and important, because only that fraction of delta phi, as you can see, not the entire delta phi, but only that fraction of the delta phi is sufficient for A plus to move from the OHP till the top of the summit. And again, we are saying that once it reaches the summit, we have put it in the right place. We have provided it enough energy. Now it is purely a probabilistic event whether it rolls over and forms the product or rolls back and goes to the reactant. That is purely a probabilistic event. So now essentially the argument that we are building is, even though there is a large delta phi that is existing, only a fraction of that delta phi is actually used up in contributing, it makes a meaningful contribution in either helping or retarding the reaction. That is, in taking this A plus to the summit. So that is what we okay, I would use alpha and beta interchangeably. So please remember, this is alpha. Okay, so that part, that fraction of the total potential drop that we are using for the reactant to take in order to take the reactant to the peak of the energy summit, the summit of the energy profile, is what is called as alpha, and you can define it as distance across the double layer to the summit, okay, divided by the distance across the whole double layer. So that means, what is the distance across the double layer to the summit, which is only alpha times delta phi, alpha times delta phi. So that means this this is essentially what we are writing is alpha delta phi divided by distance across the whole double layer. The potential drop across the whole double layer is delta phi, which essentially means alpha. And here we call alpha as the symmetry factor, okay. So that means the electrical contribution, oh god, why am I writing, sorry, this is alpha delta phi f. Okay, different textbooks write alpha, some textbooks write alpha, take it as alpha, some textbooks take it as beta. Again, there is a notation, symbol problem. Some books prefer alpha, some books prefer beta, so please be careful when you read, depending on which textbook we follow. I think I am more or less consistent with alpha. If at all I find beta somewhere, I will change it. Okay, so let's take alpha as the symmetry factor. Is this concept clear to you? That means the electric potential, that is, say for example, if you have a 10 volt per meter drop across the interface, which is very small, in reality the drop across the interface is something of the order of 10 power 6 to 10 power 9 volts per meter. Okay, if you have that kind of a huge drop across the interface, the reason being that we are considering only 3 nanometers spatially. Okay, so for a small distance you have a huge potential drop. So that means if you have a delta phi drop across the interface, from starting from the interface to the OHP, only a fraction of the delta phi is actually used up by the ion, is taken up by the ion in moving from the OHP to the peak of the energy summit, peak of the energy profile, the summit of the energy profile. And that, what fraction of that potential is used up is what we call a symmetry factor. Is this does this make sense? Perfect sense.
Subbu, what is meant by summit?
Pardon? You have to speak louder. I'm not able to hear you. Maybe I don't.
Do you mean the top of the energy profile?
Pardon?
By summit, the word summit.
Yes. The top of the energy profile, which is basically the transition state.
So distance. Could you explain what exactly the distance across double layer to summit? And could you show what that distance is?
Okay. Yeah. I'll show that. Yeah. Just a minute. I already had a slide. Okay. So see, for example, you take say something like this. Okay, I'm not good at drawing this, but I'll try. Okay, so this is the transition state that we are forming. This is the reactant. This is the product. Now you are superimposing this on a distance profile, which is basically like this. So this is the free energy profile, and this is the potential profile. When I say both potential, by superimposing, I'm saying that this is the distance of the electrode, distance from interface. Okay, distance from interface. So this is x is equal to 0. This is x is equal to 3 nanometers. Now this is all. So what I'm saying is that you have what you need to essentially do if you want to convert reactant to product is basically take this reactant and travel this distance towards the electrode. Travel this distance towards the electrode. Now, once you reach the transition state, whether it goes over to product or reactant is a probabilistic event. We are not looking at that right now. But all you are doing is taking this reactant from here and moving this distance closer to the interface. Okay, then that means because the potential profile and the free energy profile are overlapping, you need to move the same distance in the potential energy profile also. And then if you look at how much energy you have not used up the total delta phi, which is actually available to you, but you have only used a fraction of the delta phi, which I call it as, that fraction is what I label it as the alpha. So the alpha of a fraction of delta phi is what is what is used up in moving this reactant to the transition state.
Yeah, got it. Yeah, got it.
Yeah. So that is what I call it as the symmetry factor. The reason why it is called symmetry factor, the terminology, we will come to it later. Just take it for the time being that it is called a symmetry factor. Okay, it can be called anything, but there is a certain reason why it is called symmetry factor. We'll come to that. Okay. So then what am I saying? I'm saying that distance from OHP to summit divided by total distance. That means I'm distance from OHP to summit. What is the energy profile I've used up? What is the potential energy profile that I've used up? I have used up alpha delta phi. And the total distance, you have a potential drop of delta phi, which is basically nothing but alpha. Okay, so this is how symmetry factor is defined. Is this clear?
Got it. Yeah, got it.
Okay, clear to everybody? Please speak up, please.
Yes.
Okay.
Yes,
So
Subbu.
this alpha delta phi, that is the fraction. Definitely, I'm right away stating here that alpha has to be less than 1, or at the most can be equal to 1. That's all. If your energy profile is very skewed towards the interface, then alpha can be approaching 1. But definitely, from the very definition itself, you see that out of the total basket, you have a basket of fruits. You are going to take only a few fruits from that. So that means out of the total delta phi that is available to you, you are using only a fraction. Automatically, that means that alpha has to be less than 1. Yes, that is very clear. Let us get it. Let us put that down and get simultaneously get it out of make that statement. Okay, validate that statement right away. That alpha has to be necessarily 1. You can't have alpha greater than 1. Absolutely not possible. If you have energy equivalent of delta phi that is available across the interface, and you need energy which is more than delta phi, the energy equivalent of delta phi for it to cross over the summit, then the reaction is not going to happen. Finished. End of the story. Okay, so because we are seeing that the reaction that we are saying is happening, we are saying that only a fraction of the delta phi is actually used up in moving that reactant to till the summit, till the peak of the energy profile. Okay, and therefore the electrical contribution to free energy of activation. So far we have said that this is the potential, that is a fraction of the potential that is available. So if you want to convert that fraction of the potential to energy term, all you need to do is multiply it by farad. So alpha delta phi, which is the fraction of potential that is available, multiplied by the farad, because you can multiply it by the fundamental charge if you are talking about one ion. But now since we are talking about a mole of ions, we are multiplying it by farad. Okay, we are not just interested in one ion, but we want to we are interested in transferring or reducing a mole of ions or whatever the concentration we are talking about. That's why we multiply it by farad. Is this clear?
Yes.
Yeah. So then with this, now this is central, because remember what was the story that we built up here. This is the step 2, the react effect of electric field on the rate of the reaction. So we are trying to get towards that by saying that the electrical contribution to the free energy of activation, that is given by alpha into delta phi into F. So then we can write the total delta G naught as a chemical term, chemical contribution, sorry, which is delta D naught C plus an electrical contribution, which is given by alpha delta phi F. Okay, this is again delta phi is this. Okay, delta phi F. So here this delta G naught represents the total energy, free energy of activation, which is in turn deconvoluted or split into two terms, one containing a chemical contribution, another containing an electrical contribution. That is what we have through this argument made it. Now I want you to each and every one of you to be absolutely comfortable both with the fundamental treatment and also the math part of it. Math follows. I believe that math follows from the fundamental principles, or vice versa. Sometimes math can lead to very beautiful fundamental insights. But in this case, at least the math of it is following the fundamental principles that we have discussed. So if we are absolutely fine with the concept, then the math is very easy to follow from there. Is this fine so far? Yes.
Yes.
Okay. So then let us now go back. Now that we have managed to write it in terms of numerical parameters, we have still not got into what is alpha symmetry factor and all those things. Let us hold it there. Okay. But nevertheless, we have managed to write the total free energy of activation into a chemical contribution and the electrical contribution. So all that is required for us to do is take this sum of chemical contribution and electrical contribution and plug it into the overall rate of the reaction. Okay, the overall rate of the reaction, which is where is this? I messed up my slides. Sorry, I messed up my slides. What the hell? Oh my god, where are the slides? Seem to have messed up the slides. Sorry, I have deleted some slides. I don't know. 1 minute, just 1 minute. Give me 1 minute. Yeah, this slide is missing. I don't know why. Okay, let me just take it and put it here. Yeah. Okay, so then, sorry. So then, once we have done this, that is, sorry about that. So once we have done this, that is split our delta G naught, the total delta G naught, into a chemical contribution and electrical contribution, we can go forward and say that because we know that the zero field rate of the reaction we have already defined nu C, that is KT by H exponential minus delta G naught by RT into CA. And now we have written, what we have done is we have written this delta G naught in terms of a chemical contribution and an electrical contribution. So then we can use the same formalism as a zero field rate of the reaction and say that the electrochemical rate, that is, I'm distinguishing it from a chemical rate by using nu E as the subscript, not instead of C, and that's why that represents the electrochemical rate, which is nothing but KT by H exponential. Instead of delta G naught here, I'm going to replace the delta G naught by this expression. Delta G naught C RT minus negative of delta G naught C RT exponential minus alpha F delta phi by RT into CA star. Okay, all I'm doing is I'm replacing this with this summation, chemical plus electrical contribution. All that is all I'm doing, and that now signifies to me the electrochemical rate. That means nothing but the number of moles, because we have used farad. We can say talk about number of moles reacting per unit time per unit area also, because remember, go back, we said that whenever we talk about an electrochemical rate for this course, because it's a heterogeneous rate, it is not only normalized to time, it is also normalized to area. Okay, so that's why we have put per unit time, number of moles reacting per unit time per unit area, which is nothing but nu E going to be equal to the chemical term plus the electrical term. Or in other words, you have a chemical term and an electrical term, which is both sitting in the exponential, and then multiplied by the concentration of A plus. Now, in doing so, this zero field rate of the reaction is at time t equal to 10 power minus 14 seconds. And now from there, we have gone to define t equal to 10 power minus, even if I say 6 seconds, microsecond, it's very well valid, because anything beyond 10 power minus 10 seconds, you have the electrochemical rate. You are no longer talking about purely the chemical rate, because electric field is non-zero, EDL is non-zero. So you are talking about the electrochemical rate, which we have defined it in this way. Then what we can do is this kT by h exponential minus delta gc, delta g naught c by rt is nothing but the chemical rate. So here we are actually writing this nu e in terms of nu c exponential the electrical contribution. So nu c into the electrical contribution. And this signifies an extremely important relation. It is actually the marriage between chemistry and electrochemistry, because it is as important to understand in the kinetics as your delta, the connection between the thermodynamics and electrochemistry. What equation represents the connection between thermodynamics and electrochemistry? What is the equation that represents the connection? That is the single most important connection between thermodynamic parameter and electrochemical parameter. What is that?
Nernst equation.
Nernst, where does delta G not come here? Or thermodynamics come?
Delta G is equal to minus RT ln K.
Minus RT ln K, or in other words, delta G naught equal to minus NF E naught.
Yes, yes.
Yes. So that equation, that is the central equation which directly connects your thermodynamic parameter to an electrochemical parameter. Here we have now got to that kind of a situation where we are marrying the chemistry with the electrochemistry. That is, the chemical rate constant and the electrochemical rate constant are now married to each other, are now completely connected with each other. They are connected through a very strong bond. That means whenever you are talking about an electrochemical reaction, there is an intrinsic chemical reaction that has to be accounted for. So this equation is in that sense is very important, because it marries it connects the electrochemical rate constant rate of the reaction, electrochemical rate of the reaction to the chemical rate of the reaction, and of course contains an electrical contribution also. So now, because these are all rates of the reaction, remember these are electrochemical rates of the reaction. So what do we know about the rate of the reaction? We already saw that the rate of the reaction is nothing but the J by F. Yes, we already saw this. The rate of the reaction is nothing but I by NAF. And so I by A is nothing but current density J. So J by NF, if N is equal to 1, then you can put it as a J by F. So the rate of the reaction is now J by F, and this is the electrochemical rate of the reaction, because we are talking about number of farads and number of electrons, farads, the current density and all those things. So this is the rate of the electrochemical rate, and here we have defined the electrochemical rate in terms of chemical rate. So all you need to do is just take this nu E out and put it by J by NF, and then you will get it as, so that is exactly what I have written. You can add N because N is taken to be 1. So here we are talking about electrochemical current density. So we have to put in J equal to NF nu E. So here N can be written. So NF nu E, and so that means instead of nu E, you substitute this nu C exponential minus alpha F delta phi by RT, which becomes then if the farad becomes there Kc into Ca plus. Now we are saying that nu C is again Kc into Ca plus, that is the chemical rate constant into the concentration of the reactant exponential the electrical contribution. So now, is this so far clear? We have just only done what I call as mathematical jugglery. We have found out equations. So till the last slide is what the fundamental concept. This is all purely mathematical derivation. Yes. Yes, please. Anybody has something to say? Yeah. Yeah. Is this clear? Janta, please. If you want to speak, speak. I can't hear something. Somebody is speaking something, but I can't really make out what it is. Is this clear?
Yes, it is clear.
Yes, yes.
Okay. So now, if you see, I'm just going to connect, look at, identify some things here. This is the current density. This is the Faraday current or the Faraday current density. This delta phi, what is this delta phi? This is the potential that you have that is felt across the interface. And this like I said, delta phi can come either from the surface charge of the metal itself, or when the metal is connected to a DC power supply, what is the charges that you are dumping or taking out, that is what contributes to delta phi. So this in essential, if you are connecting the electrode to a potential supply, DC power supply, this delta phi signifies the potential drop, not which is actually the potential drop across the interface, actually signifies the potential that is applied from the external source. Okay, the potential that is applied from the external source, and then you have the concentration of the reactant and the product. So this equation actually connects the three parameters which is of our interest: the Faraday current density, the potential that you are applying, and the concentration of the reactant and the product. If you want, you can write it in terms of product also. Okay, then what do you see here? What do you see here? You see something beautiful, that your potential, the current density that you would expect from the reaction is going to be exponentially dependent on the delta phi that you apply. It is not a linear relation, but rather an exponential dependence on delta phi that you are. If you apply delta phi, the current density is going to vary in an exponential fashion, provided the concentration of the reactant is the same. So let us now try to write it in a semi-qualitative graphical sense. So I'm taking the mod j here, that means the modulus of j, and I'm plotting it as a function of modulus of delta phi that I have created across the interface. So remember, this is the interface. I'm looking at in this case, A coming in and going over to D. Okay, it's a reduction reaction still that I'm considering. So that means at the interface, the rate of A going to D depends on, and now I've connected this to a power supply, DC power supply. The other electrode is sitting somewhere. I'm not worried about this. It is enough if we discuss one electrode, the other electrode is going to follow the exactly same principles. So then if I'm connecting this and I'm generating a delta phi, from the mathematical case, what we see is that it is an exponential dependence. And this is again driving us to another fundamentally very interesting or important concept in electrochemistry, which is called principle of causality. It's called principle of causality. This, although we are saying it in electrochemistry, it is universally applicable. You go and hit somebody sitting next to you, you are doing an effect. You are doing an effect on the system. You will get back you are doing a cause on the system. That means you are doing an action on the system. Somebody sitting next to you, you will get the effect back. Whether that person decides to hit you back or run away depends on who you are and who that person is. But nevertheless, if you do an action, you will see a reaction. And that is the central principle of causality. How many of you have seen this movie Matrix? I know it's probably not your generation movie. Have you seen this movie Matrix? Matrix Part 1, then Matrix Revolutions, and something else. The Matrix trilogy. There were 3 movies. No? Arey, this is not a complicated question. Please answer.
People are raising hands, so.
Yeah?
Those who have seen it are raising their hands.
Pardon?
So they are raising their hands.
Oh, raising their hands. Okay, okay. Oh, very well. Raising their hands. Okay, okay. You can please unmute yourself and yeah, Shivam is raising. I can see some hands raised. So the matrix. If you see, I think I don't remember the second or the third part of matrix that talks about principle of causality. So it's not this something that we are looking at only electrochemistry. It is a universal principle, just that we are applying it to electrochemistry. In here, what is the principle of causality? For if you do an action, there is bound to be a reaction. That is the principle of causality. Okay, there is bound to be a reaction. It at some level, fundamental level, it also connects to the what really every religion says. If you do a reaction, if you do something, if you do an act, you have to face the consequence. So that's exactly the same thing. Okay, here the action that you are doing is controlling delta phi. You have the ability to control delta phi. That means I have, because I've connected it to DC power supply, I can now control delta phi. And what happens when I change delta phi? My current density starts to change in an exponential fashion. That is exactly what math, the formalism that we derived in the last slide tells us. If I change my delta phi, my j is going to change in an exponential fashion. So by taking the mod of both, we are plotting it and saying that this is the exponential behavior that we are going to see. That means for this conversion of a plus e going to d, we apply a small cause or an action. This action, that means we are changing the delta phi by a small amount. What is the effect going to be? The effect is going to produce a huge change in current density, huge increase in current density. The action of changing the delta phi by a small amount produces a huge change in the current density. Thereby, the rate of the reaction is significantly altered. And this is a very powerful tool. If you want to do it in purely kinetic terms, chemical terms, how do you affect the rate of the reaction? You either change the concentration of the reactant or the product, or you start changing the temperature of the reaction of the product, or yeah, that's the only two ways you can see. Or maybe you can use a catalyst to increase the rate of the reaction. But here we are talking about the same system. By changing the by applying a cause, or by doing an action on the system in terms of manipulating the delta phi, the electric field that is created at the interface. By manipulating the electric field that is created at the interface, you are significantly changing the kinetics of the reaction, which in turn is manifested as change in the current density of the Faraday current density. Change in the Faraday current, or in other words, increase in the Faraday current density. So then, what is this also leads us to another important question. I'll just complete this argument and stop here. Okay, please bear with me. So now, if you do this causality, or if you do this action not continuously but only at one instant of time, that means you are just like I gave the example of hitting somebody close to you. It is not, you are not constantly hitting. You hit it once and then leave it. That means the equivalent of that in our system is you switch on the DC power supply, you rank up the power supply, and then stop it, switch it off, disconnect it from the circuit. Then that is an impulse. What is it that is going to do if you do this? Say, for example, this particular reaction, reduction reaction. So we are saying that there is a you are lining up charges on the interface, and now when you line up the charges and then stop it, then the charges that is lined up is getting used up in driving the reaction from A to D. The reduction of A to D is going to reduce the charge on the metal surface, on the electrode surface. This consumes the charges that you have put in on the electrode surface, and therefore that is going to lead to the delta phi is going to reduce. Remember, you are not doing it continuously, but you are doing it as a one time process. That means you are hitting the interface with a pulse of voltage and then stopping the voltage. You are reducing the voltage all the way to zero. Okay, you are disconnecting the power supply from the system altogether. So then when that happens, that instant when the pulse is delivered, the rate of the conversion of A to D becomes increased, and that means that the once the rate is increased, it consumes the excess charges that is delivered during the pulse. That means the charge on the metal surface is depleted. That in turn reduces the delta phi. That means the delta phi becomes zero, or tends towards zero, and that means the J also closes down to zero, and this means that that particular reaction ultimately stops. Do you get this picture? Do you get this picture?
Yes.
Yes. Okay. So then that means this particular reaction ultimately goes to completion. This is why we insisted that the potential penalty that you pay to the system, the action you are doing to the system, cannot be a one-time event, cannot be a pulsed event. It has to be a continuous penalty that you are going to pay. Remember, go back to the previous couple of classes before, or couple of interactions before. We said that over potential, two things we said about over potential. It's a persistent demand. Okay, it's a persistent demand, and it is a continued penalty. It is not a one-time penalty. We see that how beautifully it wraps up the mathematical treatment that we have done, points to the same conclusion. Okay, this is a case example where the math is actually helping us conclude something. So there are two ways. One, you make the argument, and you make the qualitative argument and then convert it to quantitative mathematical terms. That is something which we saw earlier. And now, because of that math final form expression that we get, we can also it can loop back and lead to the fundamental concept that we discussed earlier. It reinforces the concept that we discussed earlier, that over potential cannot be a one-time penalty. It has to be a continuous penalty. That means as long as you are interested in driving the reaction, or interested in driving the non-zero current density in the system, you will have to do the action of paying the penalty, and that penalty is the over potential penalty. Is this clear so far? Anything that we discussed today is not which I need to repeat or something, please let me know. We will stop here, okay, for this session. But anything that we are anything that is not clear, please speak up right now, or later maybe in WhatsApp, anything. But please do speak up through some way. Just don't assume that, yeah, thanks. Okay. Yeah. Oh, I see that Ayan is showing something, and Priyanka. Yeah. Thanks. Good. Thank you so much. Okay. So if this is clear, then it's going to be easy. Himanshu, thanks. Yeah. It's going. I'll stop the recording. Okay. So